Alright, hello everyone. How are we doing today? Alright, so yesterday we had started the topic of, I think Saturday we started the topic of capacitors. So today we'll be carrying forward that discussion. Alright, so first of all, let me welcome you guys to the Unacademy JEE English. This is a brand new channel by Unacademy, which is India's largest online learning platform for IIT JEE. And here, everything is being taught to you completely in English so that all the students who are uncomfortable with Hindi can feel at home here and understand all their concepts well enough. Hi Vineet, how are you? Hello Harish. So before we move forward, let me introduce myself one more time. So my name is Rohit Dixit. I study mechanical engineering from IIT Delhi. I have been teaching for IIT JEE for more than 7 years now, and wherein I have taught at some of the biggest institutes which are there in the JEE coaching industry. Okay, I myself was JEE rank 447, and I've already coached many students to top ranks. All right, and let's hope that I can continue doing that on this new online platform. All right. Hi Pratiksha, how are you? So, as you guys know that because of all the lockdown and everything that happened, so the entire education industry has taken a shift from offline institutes to online. All right. So me included, I was earlier till now, all the teaching that I did was in offline. This is my first online venture. So what I find useful is that somebody like Unacademy is providing you such a huge platform for online learning, and it gives you its subscriptions which have great benefits like live classes. You have get to interact with your educators. You have live polls and leaderboards. You have test series and analysis, and you have live doubt clearing sessions. So trust me, with this kind of a structured course plan here, you do not feel that you're missing out on education, even if the entire thing has shifted online. The Unacademy platform gives you a great experience, which is very equivalent to your any offline setup. All right. Plus, of course, they have got India's best educators on a single platform for you. So now, yes, it is possible for all of you to get access to the best educators in India sitting in the comfort of your home. I mean, imagine me sitting here in Delhi. I'm able to reach out to students all over India, which is just amazing. All right. So how do you get this Unacademy subscription, and how do you make most of its benefits? So it's very simple. You install the Unacademy app. Once you have installed the app, then you go to the plus section, you select your goal as IIT and click on get subscription. That is how you can get the subscription of Unacademy. Now, if you look at the pricing of the subscriptions, they get very modest. So a 12-month subscription comes at a cost of 2,500 a month, and 24-month subscription comes at 1,500 a month, which is 50 rupees a day, which is nothing compared to the all the fees that you might be paying elsewhere. And so this is a way of Unacademy trying to provide you high quality education at a very reasonable and affordable price. Now, this can be made even more affordable if you use my code RDLive to get your subscriptions. So if you like my lectures, if you want to enroll in my courses on Unacademy, then you can get your subscriptions using this code RDLive. This will give you an additional 10% discount also in your subscription fees. Alright, please remember that those of you who are following us on the JEE English channel, you can connect with us on the Telegram app using the link shown above, so that you're not missing out on any of the notifications of about any lectures and sessions happening on the JEE English channel. You can also connect with me on the Telegram. You can, if you want to get in touch with me, you can find me on Telegram using this. This is my user ID on Telegram. Okay. I don't think there are lags. Okay. Pratiksha, yes, I am on the platform. I am on the Plus platform, but I still haven't started any courses, regular courses yet. I'm only conducting special classes so far. Okay. Oh, good to see you, Ankit. All right. So Ankit is one of the most regular students of mine. I really appreciate that. All right. So without any delay, why don't we continue with today's discussion? So so last time I introduced capacitors. I told you how you can define capacitance for an isolated conductor, how you can define it for a system of two conductors kept nearby. Then we looked at some common configurations. So let's just go through that. So we discussed last time. Very soon, Ankit. very soon. I'm still waiting. There is some bit of coordination and some bit of planning happening on the part of an academy team also. So as soon as they give me ready to go, I will launch my courses. Okay. All right. So last time we realized that the most common configurations of capacitors are of three types, which are called parallel plate, spherical configuration, and cylindrical configuration. And we also derived the formula for the capacitance of such configurations. All right. How to do HCV effectively? Okay, so you solve all your problems starting from the objectives only, and do not look at the solutions. That is the most effective way. All right. Okay, I will definitely. Uh, so yeah, I remember when I did HC Verma as a student. Okay, so I would solve each and every problem, each and every part, and even if there was a part which I could not get right immediately, I would maybe think about it again, maybe take a break. If I don't think I'm thinking on the right lines, then I'll probably take a break and attempt it again. But trust me, I think maximum it took me ever was two attempts for any problem. I could solve them in maximum, attempting it twice. So that was it. So I think that's a good way. So you try on your own. You try and understand the problems on your own and solve on your own only. And if you can't, then discuss them with your teachers. Have a discussion over them. Don't look at the solution. You may look at the solution. You may figure out, okay, this is how you solve it, but you may still not understand why you did not get there. All right. So it's always better to discuss solutions with your teachers. Okay. I hope that answers your question, Aryan. All right. So, anyways, so we realized last time that these are the formulae. I hope you know how we got these formulae. In case you haven't, you don't know, then you can watch my previous video on the first video on capacitors, wherein I have shown the derivations of all these formulae. How this comes, and how this comes. All right. So these are the three configurations. And before we move forward, let me tell you some important points. Okay. So if one of the plates of the parallel capacitor slides relatively, then C decreases. So please remember, so earlier what I considered was that the two plates were identical and they were exactly placed in front of each other. So in that case, the area that you take in this formula, C equals epsilon naught A over D, is the complete area of the plate. But suppose if the case is like this, that only the plates are partially covering each other's area and some areas are blank. Then the area in the formula is only this. The overlapping area only is considered. See, I'll tell you what the logic is. The logic is that what were you doing when you wanted to make a capacitor? You wanted to store electrical fields. So you only consider the charge whose electric fields you are storing, and you only consider, that is why you only consider the area in which the electric fields are getting stored or trapped in here. All right. So even if you had one plate like this and another plate like this, then the area would be taken like this only. Only this area would be considered. So if this was area 1, this was area 2. So in such a case, here in your formula, this would be A1. Okay, you will only take A1 here. So these are some important points that I wanted to tell you in case you have some variation of configuration. All right. Next, both the plates of parallel plate capacitors, if they are touched, then what happens? Then the resultant charge will obviously become zero and the potential difference between them will disappear. Alright, so make sure if there is a wire, if both the plates are connected with a wire, then everything disappears. Then the charges from here to here will flow and the electric field between them will disappear. There will be no potential difference. And the capacitance, obviously you cannot define the capacitance of any uncharged thing. So it has to have a charge. Alright, so you won't be talking about that. Or you can do it, but it will be done in a different way. This no longer is a capacitor, first of all. Why? Because you cannot store fields here now. You cannot trap and store fields. Alright, so I hope you remember that I had told that the capacitor is a device which is storing energy. And how is it doing that? It is storing electric fields, and electric fields carry energy. So those of you who don't know how electric fields carry energy, we will talk about that. But I had already mentioned it in my second class when I was introducing the concept of electric fields. There I had already told that electric fields carry energy as well as momentum, by the way. So here I'm not interested in momentum, I'm just interested in the energy stored in the fields. So how do we calculate that? We will talk about that. I think I had already mentioned the expression that du over dv, which is the energy stored per unit volume in an electric field, is given by half epsilon naught E dot E. So this is the expression for energy stored in an electric field. And I'd already told you, whenever you get two charges close to each other, then this field modifies, and the electrostatic potential energy that comes is actually stored in the modified field. The energy stored in the fields changes. Well, it may increase, then you have positive potential energy. It may decrease, then you have a negative electrostatic potential energy, which is also called the interaction energy. Anyways, for that, you can again visit my previous videos. Alright, so here. So if you realize that we are always considering the electric fields to be parallel. Alright, why? Because we took the assumption that the plates are infinite. Remember this. I hope you saw the derivation of parallel plates. There we took an assumption that the area or the dimensions of the plates are much greater than the distance between the plates. Because what happens because of that? In that case, I can consider my plates to be infinite, and I can conclude that the electric field here inside would be uniform, alright, and perpendicular to the plates. However, what happens when you're approaching the edges of the plates? When you're approaching the edges of the plates, you will realize that the curve, these field lines start getting curved towards the ends. So they will be straight for the middle parts, but towards the end they start curving like this. So this is called fringing, by the way. This field is called fringe field. Alright, so these fields would be almost negligible compared to this uniform field if our assumption is true. So as long as my assumption is true, I do not need to bother about these bending electric field lines. Okay, so please note that non-uniformity of electric field at the boundaries of the plates is negligible if the distance of the plates is very small compared to the length of the plates or the dimensions of the plates. So if my assumption is still valid, I can ignore the effect, ignore the end effects. Okay. Alright, so now let's talk about the energy stored in a capacitor. Alright, this is something new that we will discuss today. So I've been telling you repeatedly, even the definition of capacitors is that it is a device used to store energy. So how much energy is it actually storing? So let's take a look over that. So when I connect it to a battery of potential difference V, okay, a voltage V. So when it is connected to a battery of voltage V, it produces a potential difference between the plates, which is also equal to V. Okay. Why? I mean, see. So if you have this positive terminal, if you have this negative terminal, when you connect a capacitor to a capacitor essentially has two conducting plates, metal plates. All right. So the moment I connect a metal with anything, then it always acquires the potential of that thing. So let's say if the potential of this positive end was V and if this negative end was 0, so this plate will acquire a potential of V and this plate will acquire a potential of 0. Alright. So whenever you touch a metal with something, it acquires the potential of that thing. So, and as a result, what will happen is that there will be an electric field between them. How is that getting there? Essentially, the battery is providing some plus Q charge to this end and minus Q charge to this end. So I can say battery is making a Q charge flow from this end to the other end. That is the job of battery. That is what the battery has to do in order to create the potential difference between two plates. The battery takes some charge Q and places it on the other plate. Alright, so plate at the higher potential will get a positive charge, plate at the lower potential will get a negative charge. So when a capacitor is connected to a battery, it stores a charge. So you can see when the moment I did that, now both the plates have got plus Q and minus Q charge, which is called the charge of capacitor. Whenever somebody asks you what is the charge of capacitor, you always mention the charge of either of the plates. Please remember that the total charge of the capacitor is always 0. So when I ask you what is the charge on the capacitor, you don't say 0. Okay, you mention the magnitude of charge on either of the plates. So you will say in this case Q. Okay. Now this stored charge in turn creates an electric field between the two plates. As I said, when you look at your plates, there will be so this will be positive, this will be negative, and there will be an electric field. And this electric field gets stored here. All right, and it gets trapped between the two metals. Now, what we can do is that this electric field is storing energy. All right, so I have got energy stored between the two plates in form of this electric field that got created. Now, what I can do is once I have charged my capacitor, I can disconnect it from the battery. It will hold this charge. It will be like this. Now, I can carry this guy anywhere I want. Okay, this is a small thing. I can carry this with me. It has energy stored. I can use this energy later. So that is how I am storing energy. So batteries also provide energy. Batteries are also sources of energy. So this is an alternate source of energy. All right, and why do we use this, by the way, when we already have batteries to provide us energies? Why do we need capacitors? It turns out they have various applications, and they have great applications where uh, they can be used in a much better manner than the batteries. Batteries have a certain characteristics. Capacitors in circuits will have entirely different characteristics, and sometimes we require those. Okay, so because its applications are very very different than batteries, that is why we this is an alternate option of storing energy. All right. So once I have charged capacitor, now I can take it with me. I can move around with me, and whenever I need this energy, I can discharge the capacitor. All right. So in charging of a capacitor, I'm storing energy in it, and when I need that energy, then I'll discharge that capacitor across some circuit element, maybe across a resistor. I can connect it with a resistor. The energy stored in the capacitor will flow through the resistor. So that is the point. So I wanted to store energy. I have stored energy. So and once I've stored energy, I can disconnect this from the battery. I can take roam around with it, take it anywhere that I feel like, and I can use this energy later. All right, that was the idea. Now I'm saying that the energy stored in a capacitor can be given by Q square over 2C or half CV square or half QV. So how are we getting this expression? This is the amount of energy which gets stored in a capacitor. So where Q is the charge on the capacitor, C is its capacitance, or V is the potential difference between two plates. So you will realize all these three equations are one and the same because you can use the fact that Q equals CV. So if you use Q equals CV, then you will realize all three are the same. All right. Sir, for us, school start from September 5. Okay. Okay. Yeah, most probably. I had heard that they plan to open schools from September. All right. So let's find the expression and how am I getting this expression. So imagine this. Imagine that at some time this is at 0, this is at some plus v, and at this time, okay, this let's use some different name. This let's call this v1 because v I took as the final potential. All right. So initially what is happening is that initially both the plates would be at the same potential. All right, because they have no charge, and after some time, let's say after some time t, then how can I watch this channel lectures? Okay, what are your school timings going to be, Hitesh? There is a reason why I start my first class at 4 because I think you can get home and watch this video even at 4. I think. What time do you get free from your school? Okay, so let's focus on this. So imagine at some time the potential of this is V1, the potential of this is 0. What has happened is that initially there was no charge. Now I started giving both the plates some charge. So this has already acquired minus Q and this is already acquired small plus Q. So I'm still in the middle of the charging. Alright, so I'm going to take the total charge from 0 to capital Q. So this is a middle stage where I have reached a charge of small q. Okay. All right. So consider this. So at this time, if I consider that the potential difference is V1, essentially what I'm doing is I'm transferring charges from this plate to this plate, right? So when I want to charge, when I want to transfer an additional dq charge, imagine if this already has a minus q charge, this already has a plus q charge. Now I'm taking an additional dq charge from here to here. So I have to do work against this electric field, or there is a potential difference. So the work required to transfer this dq from here to here. What will that be? Potential difference was the work required per unit charge. So I can say that the work required in transferring an additional dq would be v1 times dq. Alright, I hope you guys are following this. That at some instant, while charging, if this plate has acquired a minus q charge, this place has acquired a plus q charge, and right now the potential difference is v1, then at this time, imagine I want to transfer an additional plus dq charge from this plate to here. So I will need to do work against this potential difference. The potential difference between two plates is v1, and I know my definition of potential difference. Potential difference is the amount of work required to take a unit charge from here to here. So how much charge am I taking? I am taking a dq charge, so the work required would be v1 times dq. Alright, I hope everyone's with me till now. Alright, so now I can say also how much is v1? v1 can be written as q over c. At any time, if the charge on the capacitor is small q and the potential difference between the plates is v1, then I can use this relation. Okay, so v1 can be written as small q over c. Now let's substitute this value here. So let's see what am I getting. We get dw equals small q over c times dq. So this is the small amount of work required to transfer this charge dq. Now we started from q equals 0 and we are planning to go to q equals capital Q. So let's see what is the total work required to completely charge an uncharged capacitor. So the total work required to completely charge this uncharged capacitor would be integration of this, and the value of q I will be taking, I will start with q equals 0 and my aim is to finish at some capital Q. So let's see what is the work required. From here I can say that work required is 1 over c q square over 2, that is the integration of q going from 0 to capital Q. So you're getting your work as q square over 2c. So whatever work I am doing in charging these plates, that is the work that will get stored in form of the energy. Alright, so I hope you follow this. This is the expression that I'm getting. The whatever work I'll be doing in charging this capacitor is the where is this work going? This is the work that is getting stored in form of energy, in form of electric fields. Alright, so now I can do all these substitutions. Alright, I know that since I can say q equals cv, so I can say that w can also be written as half cv square or half qv. Alright, so these are the three expressions that we can use. So you can use any of these depending on what has been given to you. If q and c have been given to you, then you use the first equation. If c and v have been given to you, then you use the second expression, and so on. Alright. Now, I had told you that this energy is getting stored in the electric fields. Okay, so now I know the total energy stored. Now I want to derive an expression. I want to derive an expression of the energy density in the electric field. So how much energy is getting stored in the field per unit volume? So where is this energy? This is in this volume. Alright, the volume between the two plates where the field is trapped. So what is the volume of that? The area of cross section each plate is A. The distance between the two plates is D. So the electric field is present in a volume of A times D. I hope you guys can see that. So if I make a figure like this, so this volume. Okay, let's use some a different pen. So this volume between the two plates. What is this volume? This volume would be A times D. Alright. So we know that E is present in a volume of A times D. Alright, so this is the volume in which the field is present. Alright. Now, I know how much energy is stored in this volume. What is the energy stored? Also, I know the energy stored U is half CV square or half Q square by C. Let's take to half Q square by C. Alright, now what I'm going to do is that I'm going to substitute the value of C for a parallel plate capacitor. So I also know how much is C. So since C equals epsilon naught A over D, let's start substituting this value. I can say that U equals 1 by 2 Q square over epsilon naught A times D. Alright. Now what I do is, now please pay close attention. I will multiply this side with epsilon naught A and divide it by epsilon naught A again. Alright, let's see what that gets us. So on this side, what do I have? I have 1 by 2 epsilon naught A times D. Alright, so I'm taking this together and then I have Q square over epsilon naught square A square. Alright, so I can break it like this. Now, what is this? If the plate had a charge density of sigma, plus sigma here, minus sigma here, I already know what is the relationship between sigma and E. I know E equals sigma over epsilon naught. I had shown this in the last lecture also. And I know sigma is Q over A. Alright, I hope you can see that. Sigma is nothing but the charge per unit area, charge density, which is Q over A. Now look at this. This is Q over A whole square. So this is sigma square over epsilon naught square. Alright, what is sigma square over epsilon naught square? And that will be E square. Alright, I hope everybody can see that. So now I can rewrite this as U equals 1 by 2 epsilon naught. And I can write this as the volume. A times D I know is the volume into volume. Let's use some different symbol for volume. So let me just write volume only. Into this will come sigma square over epsilon naught square, and I can replace sigma square over epsilon naught square by E square. So if I take my volume here, if I take my volume to the other side, U per unit volume becomes half epsilon naught E square. That is the expression that I was looking for. So that is the energy density of any electric field turns out. We derive this expression with the help of capacitor, then we use this expression anywhere because there is no reason why the energy density of electric field or the basically the energy stored per unit volume in electric field should be different here and should be different elsewhere. It is an inherent property of electric field. So if electric field stores this much of energy per unit volume here, then it should be storing this same amount of energy per unit volume anywhere else. Alright. Okay, so please note one thing. Here I am getting this. The energy density in the entire region is constant. Why? Because the E is constant. If E was variable, then you take small volumes and then you say the differential form of this can be written as du over dv equals half epsilon naught E vector dot E vector. So even if your field was varying, what you do is, suppose you had a field of a plus Q charge. So just imagine there was a plus Q charge and the field is continuously varying. So you know that field at different places will be different. 1 over r square, it will fall off with 1 over r square, right? So consider here you wanted to find, so you take a small volume here, dV. Alright, so you consider a very, very small volume dV. Now in this entire dV, what you do is, you can consider that the value of E is constant for this small volume dV. I am taking the dV to be such a small volume that the value of E or electric field magnitude and as well as the direction can be considered to be constant in this region. So the du, the energy stored here, so if the energy stored in this volume is du, Then your du and dv are related by this. Du over dv is this. Alright. Now you can integrate to find the total energy stored. So this is where we get this expression from. We got this expression with the help of capacitors, and then we started using this expression everywhere. And turns out it gives the correct results. Alright. Why is the value of E constant? Okay, so the value of E is constant because we are taking infinite plates. Alright. These plates are considered. Oh, in that. Yes, yes, in that we have taken it so small that in this region the variation of E can be ignored. Alright, it is such a small area that the variation of electric field can be ignored in that. Okay. Alright. Similarly, here E was uniform because you were taking parallel plates as infinite plates of infinite size, and infinite plates produce a uniform electric field. Alright, so I hope everybody followed this derivation. Please let me know if you have any doubts about this. No problem, Uncle. I hope you followed this derivation. If any one of you have a problem with this derivation, please tell me. I will go over this one more time, but this should be fairly simple. Alright, this is pretty straightforward. Alright, so I'm assuming then no issues with this derivation. So why don't we start with the problem then? So this is a practice problem. This is a straightforward formula-based problem. So to find the energy stored in a capacitor of capacitance 100 microfarad when it is charged to a potential difference of 20 volts. Alright, so find the energy stored. Just simply apply the formula. Alright, let's try this problem. Alright, Vineet, Ankit, Hitesh, where are you guys? Okay, whenever it comes to problem solving, you guys get lazy and stop responding, which is not fair actually. I'm not supposed to solve these problems. You guys keep waiting for me to solve these problems. It's you people who require the practice. Alright, why don't you try this problem till then I can get some water. So I'll give you 1 minute or maybe 2 minutes to solve this. This is a fairly straightforward. You just have to apply the formula. So try this problem till then I'll get some water. Okay. Alright, any answers? Okay. Anyhow, this is fairly straightforward, so I won't be wasting any more time on this. So, how do you solve this? This is very simple. You just learn the formula that U equals half CV square. All you had to do was substitute these values. So here it would be half into C, which is 100 microfarad, which is 10 to the power minus 6, into 20 square, which is 400. So yeah, 4 powers here gone with 2 powers here left. This is 2. So the U energy stored is 0.02 joules. Alright, this is the energy stored in my capacitor. Alright. Okay. Now let's talk about capacitors. Capacitors, batteries and capacitors in circuits. Alright, so when you have many capacitors connected to batteries, how are the capacitor circuits looking like? Alright, so first of all, let's take the simplest case. Let us see what happens to a single capacitor with a battery. Alright, so when I connect a single capacitor to a battery, what will happen? So when a capacitor is connected to a battery, as shown, it charges almost instantaneously. By the way, that is one of the very important uses of capacitors. As some of you might ask that why are we using capacitors to store energy when I already have batteries which store energy. So they both have their own advantages and disadvantages. Alright. So one great advantage with a capacitor is that it can get charged very fast. While your batteries take a long time to charge. I'm sure you know because you keep charging your phone on the time, all the time, and your phone takes up a lot of time to get charged. Alright. While on the other hand, a capacitor can get charged very fast within a matter of a few milliseconds maybe. Alright. So depending on how good your circuit is. Alright. So that is one advantage. So what you will see is that the moment you connect this capacitor to a battery, it almost gains this charge instantly. So this plus Q and minus Q would start flowing from here, and almost instantly you see that the charge has stopped flowing and the capacitor has become fully charged. Alright, so here I am taking an ideal situation. In this ideal situation, no connecting wires have any resistance. Okay, so if no connecting wires have any resistance, then of course the charge flow would be immediate. There is no hindrance, and instantly, the moment I connect these two, so instantly this plate will come to a potential V, which is the potential of this, and this plate will instantly come to a potential of 0. So the potential difference gets established instantly, and instantly the plates of the capacitor acquire these charges Q. Alright. So obviously the assumption here is that all the connecting wires of the circuit are ideal. Ideal means resistanceless. What I mean is resistanceless. So I've considered that no connecting wires have any kind of resistance. Alright. Now the potential difference between the plates, the moment this is done, the moment this is connected, I told you this plate will come to a potential of V, this plate will come to a potential 0. Alright, so immediately when you connect this capacitor to a battery, what will be the potential difference between the two plates? It will become V. So once you connect this to a battery, you will realize that the potential difference between the two plates has become V. The charge that gets stored Q would be C times V. Alright, and the net energy that gets stored is half Q times V, or half CV square or half Q square by 2C. I could have written any of the expressions. But the reason why I chose this expression was that I want to attract your attention to something very interesting happening here. You can note that the energy stored in the capacitor is half QV, which we just calculated. That is in a capacitor. But how much work is the battery doing? Now let's talk about the battery. The charge of a charge of Q essentially flows from this plate to the other plate. Okay. So think about this. The charge of Q is flowing from the negative plate and going to the positive plate. Alright. Now all this charge will cross the battery here. Here it has to go from a lower potential to a higher potential. It can always go from a higher to lower potential automatically. But in the battery what happens is that it has to move from the negative terminal to the positive terminal, and that is where the battery does work. Alright, in any circuit. Battery does work in making this charge go from lower potential to higher potential. Once it reaches higher potential, then it can go through the circuit and reach the lower potential automatically. Alright. So in moving this charge Q from 0 potential to V potential, how much work will the battery do? The battery will do on any dq that is passing will do a work of V times dq, and the total charge that passed was capital Q. So the total work done by battery would be capital Q times V. So you will realize whenever a dq charge is crossing, suppose a small dq is crossing. So dW, small work done by battery would be V times dq. This dq has to cross a potential difference of V. Okay, so when you integrate this, the potential difference remains constant. Okay, and this charge will go from 0 to capital Q. You will realize work done by the battery. Work done by the battery is V times Q. Alright. So what you realize here is that the battery is doing a work of capital Q times V. The energy that is getting stored in the capacitor is 1 by 2 QV. So my question is, where did the rest of the energy go? Where does the rest of the energy go? Alright, by the way, before you say that it goes here, it goes there, let me tell you that I have considered all the circuit elements to be ideal. Alright, so before you start making any excuses, okay, all elements are considered ideal. All circuit elements are considered ideal. All circuit elements are considered ideal. So what that means is that there are no resistances anywhere. Neither is there any internal resistance to the battery, nor is there any resistance in any of the connecting wires. So the energy cannot dissipate through that. Okay. So why don't you try and find out where is this energy going? And it's a significant amount of energy. If there was a negligible amount of energy that was getting lost, I would have been okay with that. That maybe negligible energy randomly got lost. But half the energy, exactly half the energy is getting lost. That's a huge chunk of energy that got lost. If I wanted to store E amount of energy or U amount of energy, imagine I am wasting U amount of energy also. So I need to look into this. I need to figure out where this energy went because this is a significant amount of energy. Suppose I wanted to store 10 joule of energy. My battery is doing work of 20 joule and I realize that I don't know where this 10 joule, the other 10 joule went. When battery is doing a work of 20 joule, I am only getting 10 joule. What is happening to the rest of the 10 joule? That's a significant amount of energy. I can't just let go of that. I need to figure out where it went. Okay, so you guys can try and find this out. Maybe have a discussion amongst yourself. Maybe uh, try not to Google it. Try to think about it. Maybe have a discussion with people. Maybe have a discussion with friends. Maybe have a discussion with the teacher, and ask them where is this energy going. All right. Any ideas so far? Any ideas? Any of you think of where that energy might be going? If you can, then I would like to hear your responses. Otherwise, I would like to give you some time to think about this. That where does such a huge portion of my energy go? And please remember that all circuit elements are ideal. So there is no resistance in any of the connecting wires. There is no resistance inside the battery. The battery is doing its work also perfectly with 100% efficiency. You can't say that actually the battery, while doing work, only loses its energy. No, it has been considered to be ideal, and this is a theoretical case. All right. Okay. So one common answer that people give when I remember when I was teaching offline, and I used to ask my students this question: where is half of the energy is going? And they would come back the next day, and so they probably asked their school teacher, somebody, I don't know. The answer that they would give me, that the reason they have been told is that it is impossible in real life to have ideal resistance wires. So in real life, of course, these wires have resistances, and that is where this energy disappears. But think about this. Think about this. For so far, when I'm making my calculations, when I calculated the work done by the battery, does it matter whether the resistors are ideal or resistance less or having resistance? It doesn't, right? This derivation still comes out to be this. Similarly, when I was talking about the energy stored in the capacitor, again, the role of wires is not there. So theoretically, how about a theoretical case? Fine, maybe practically I can't have completely resistanceless wires, but theoretically I can. So in this theoretical case, even if I can consider all my wires to be perfectly of zero resistance, I am still losing energy theoretically also. Alright. See, in any of my equations, I did not consider the resistance of the wires. So even if the resistance was actually zero, okay, it may not be a practical possibility, but theoretical possibility it is, right? So theoretically, I'm saying, what if the resistances are zero? Then also you're getting this result. Then also you're getting that half of your energy is getting lost. So that does not make any sense. It has to, that energy has to go somewhere. We know that conservation of energy means that the total energy cannot change. So even in a theoretical setup, I should have an explanation. even if a theoretical setup where the resistances can be zero, I should have an explanation for where this energy is going. Alright, so you guys think about it, discuss it with your friends, and try to give me an answer maybe by the next session. Okay. Alright, next, let's talk about multiple batteries connected to multiple capacitors connected to a battery. So till now we saw the behavior of one capacitor if we connected it to a battery. Now what happens when I connect multiple capacitors to a battery? Now in general, whenever multiple capacitors are connected to a battery, an equivalent capacitance of the combination of capacitors can be obtained. So I have taken up an example where there are so many things. Alright, so I can always replace all this with a single capacitor. I can say that this has an equivalent capacitance of C equivalent. And I can replace and redraw this circuit as a single capacitor which has a capacitance of C equivalent and the same battery. So how do I decide what is the equivalent capacitance? Sir, today I joined plus, say your code, sir. Okay, Jay Akash, my code is RD Live. RD Live. That is my code, alright. So as I was saying that any number of capacitors that are connected to a battery, they can be converted and I can replace all of them by a single capacitor which has some equivalent capacitance which I can call C equivalent capacitance. So how do I decide what this equivalent capacitance is? It's very simple. So what is this entire combination doing? This entire combination has a potential difference of this 10 volt across it and causes a charge of plus Q to flow from here and minus Q to flow from here. That is also what I can say. It is RD live, RD. Rohit Dixit, RD. That is my name, RD, Rohit Dixit. So R from Rohit, D from Dixit, live. Okay. Alright. So as I was saying, please remember that when I am deciding the equivalent capacitance, how do I do that? My equivalent capacitor or that single capacitor, what should it be able to do? It also, when it has a potential difference of 10 volt, it should also take up a charge of plus Q from here and minus Q from here. So then I can say that this is equivalent. See, what the idea of equivalent is, if I hide this in a box, if I keep this entire thing in a box which you can't see, you can't look inside this box, okay? I am placing a box over these. So imagine this entire setup is kept in a box. And this is also kept in a box. And you're not allowed to look inside the box. Then, without looking inside the box, can you differentiate which one is which? You can't. Okay. That is the idea of deciding an equivalent capacitance. Equivalent means that whatever effects this setup is producing, alright, the effects produced by this should be identical to the effects produced by this. So if I don't get to see which configuration I have outside, all the effects should be the same. If connected to a same battery, it should be drawing the same amount of charge. So when connected to the same battery, these two should be drawing the same amount of charge, storing the same amount of energy, having the same amount of potential difference across. So everything should be identical for these. Then I can say that the capacitance of this single capacitor is the equivalent capacitance of this entire system. I hope everybody is following me. Do you realize what I call equivalent capacitance and how I decide that equivalent capacitance? Equivalent capacitance is a capacitance of a single capacitor that can be replaced, that can replace the entire bunch of capacitors that I have, such that all the effects that the entire bunch of capacitors was producing will be produced by this single capacitor. Alright. Now, in general, when multiple capacitors are connected, Uh, to a battery, an equivalent capacitance of the combination of capacitors can be obtained. I already explained you that, how we are doing that. Now, two common combinations of capacitors are as follows. Now, you must be remembering that you studied this in class 10th. You studied a combination of resistors, and there were two kinds of combinations of resistors, series and parallel. So, similarly for capacitors also, you have two combinations, series combination and parallel combination. So, let's take a look over that. So first, let's talk about the series combination. So this is what series combination is. This is exactly like the series combination of resistors. So I hope you remember the series combination of resistors. So when one resistor is like this, another was like this was what was called a series combination of resistors. Similarly, here you have one capacitor like this, another capacitor like this, another capacitor like this, and so on. Oh, by the way, this is the circuit symbol of a capacitor. Okay, this is the circuit symbol of a capacitor. Okay, by the way, doesn't matter what kind of capacitor is it. Even if it's a spherical capacitor, you will represent it like this. This is just the circuit symbol. Alright. Hello Noman, how are you? Alright. So that is the circuit symbol of a capacitor, and this is what a series combination of capacitors is going to look like. So these are the capacitors which are connected in series. Now, I'm saying that this in this combination, you will realize that each capacitor has equal charge for any value of capacitance. Why? Let's see. If imagine a plus q charge flows from here, then a plus q will get here, and then automatically a negative q will come out to be here. Okay, let me just show you this. You remember in this case of two parallel plates, if I gave one plate a charge of plus q and I'm not giving the other plate any charge, then let's see how this charge distributes. Oh, I'm great, Norman. Thank you. So, what is the so this has been given a total charge plus q, and this has absolutely no charge. Alright, so how does this charge distribute itself? So the way this charge distributes is that obviously the total charge was plus q. So one possibility is this. Alright, that is one possibility. But here what will happen is when you are connecting it to another plate, when you have another plate, then something very interesting happens. Let me show you. When you have these three plates, now what is happening is these are so many plates. How much total charge am I giving to my system? Imagine the battery is giving plus q charge here, and the battery is giving minus q charge here. So the total charge that I am giving my system is zero. If the total charge is zero, how does the charge start appearing? Here it will be zero, here it will be zero. I know that from my charge distribution. So this was given a total charge of plus q. The entire plus q comes about here, because of which minus q comes here. If minus q comes here, and 0 will come here, 0 will come here. Why? Because these are connected. There will be no potential difference between them. Alright, so plus q will come here, minus q will come here, plus q here, minus q here, and so on. That is the kind of charge distribution that I'm going to get, which you can see here also. Alright, this system is being provided a total zero charge. Alright, so this is 0, here it is 0. This plate was given a plus q charge, so all the plus q comes here, so because of which minus q has to come here. And similarly, you can say that entire minus q comes here, so plus q has to come here. Now, due to charge conservation, these charges will appear here. So that is what you notice here. What are you noticing? That whenever you're connecting any number of capacitors of different capacitances also in series, all these capacitors acquire an equal amount of charge. Alright, please remember this, that any number of capacitors of any individual capacitance, even if all their capacitances were different. See, this at C1, this at C2, this is C3. But still, the charges appearing on the capacitors are always identical. Now I'm saying is that the equivalent capacitance for such a system is 1 over C equivalent equals 1 over C1 plus 1 over C2 plus 1 over C3 and so on. You remember this formula? This is the formula for parallel combination of resistors. So for series combination of capacitors, you are getting the formula for parallel combination of the resistors. Alright. Now how are you getting this formula? Let's also see that. Let's talk about the proof. Okay, so how can we prove that? So let us assume that I had n capacitors like this. So maybe here some more capacitors. So we had many capacitors like this. Alright, and all of them are getting a charge Q. Now what happens is that what is the entire potential difference across this? The potential difference across this entire thing would be V. What is the potential difference across this? Let's call it V1. Let's call this the potential difference across this V2 and this V3 and so on. So I can say that from the equation of Q equals CV, I can say what is V1? V1 being the potential difference across capacitor number 1, C1. It will be capital Q over C1. Alright, I hope everybody agrees with that. Similarly, V2 would be Q over C2. V3 would be Q over C3 and so on. Alright, now I also know if I add all these potential differences from here to here, if I add all these potential differences, what is the sum going to be? The sum is going to be V. Alright, so I can say that V equals Q over C1 plus Q over C2. Alright, now comes the important part. Okay, so this is for this circuit. Now imagine if I wanted to replace it with a single capacitor. So when I replace it with a single capacitor, this is V. The single capacitor should also get the same amount of charge. It should be able to draw the same amount of charge from the battery. And this has C equivalent, and this also has a potential difference of V across it. So I can from here, for the equivalent circuit, similarly, also I can say for the equivalent circuit, what I can say is that V would be equal to Q over C equivalent. Alright, for this single capacitor circuit, I can say that V equals Q over C equivalent. Now replace this value of V over there. So replacing this value of V over here, let's see what am I getting. I am getting Q over C equivalent equals, I can take Q common from here and this will be summation of 1 over Ci. Alright, so this gets cancelled and that is what my final expression is. Therefore, 1 over C equivalent is summation of 1 over Ci. So in capacitors were connected, then I equals 1 to L. This is what your equivalent capacitance formula is for series combination. So please remember this, that the formula is opposite in series combination. Alright. The formula that you are getting in series combination was the formula that you got in parallel combination for resistors. So please pay attention to this. And of course, this is a result which you need to remember. Alright, so remember this result. So that is the proof. It should be simple, pretty straightforward. Alright, not much issue with that. Next, let's talk about the parallel combination of capacitors. Okay. So this is the parallel combination. I hope you remember this is how you connected your resistors also in parallel. So in parallel combinations, all the positive plates are at the same potential and all the negative plates are at the same potential. Obviously, you can see that. Right, all the positive plates have been connected to this end of the battery. Okay, so this is positive, this is negative. So all the positive plates are connected to the plus end of the battery. So all of them will acquire the potential of the positive terminal of the battery. Similarly, all these plates will acquire the potential of the negative terminal of the battery because all of them are eventually connected to the negative terminal of the battery. So these guys all are at the same potential. Positive plates, all the negative plates are at the same potential. So the potential difference across all three capacitors is the same. All right. So the potential difference of across all the capacitors is same, but the charge would be different. Why? Because their capacitances are different and V is same. So Q would be C times V. So you will have different charges on different capacitors. Now I'm saying that equivalent capacitance can be given as C equivalent equals C1 plus C2 plus C3 and so on. Now let's see the proof of that. So as I keep telling you repeatedly, let's imagine some charge capital Q comes from here plus Q. Basically, Q is getting transferred from here to here. From here to here, Q is getting transferred. Now let's imagine that the charge that this guy is getting is plus Q. So total Q amount of charge, capital Q amount of charge total flows from the battery, out of which let's say Q1 gets here, Q2 gets here, and Q3 gets here. So Q getting here, it gets divided into Q1, Q2, and so on. And maybe if even if there were others. Alright, so I hope you can see that. Okay, so what is the potential difference across all the capacitors? So let's mark that also. So what is the potential difference across these? It is V only. Right, whatever is the potential difference across this is the potential difference across this. Because this plate and this plate, this are at the same capacitance, at the same potential, this and this are at the same potential. So across all the capacitors, your potential difference is V only. Alright, let's use the fact. And let's say, what is the value of Q1? Q1 equals C1V. Similarly, Q2 equals C2V and so on. Alright. Now, what I can say is capital Q would be Q1 plus Q2. And for whatever number of capacitors you connect, if you add the total charges, individual charges stored on the individual capacitors, I should get the total charge. So what am I getting? I am getting total Q equals C1V plus C2V plus all the charges on such capacitors. Next, let us also talk about the equivalent circuit. I told you when you join this, when you replace this entire circuit with one equivalent capacitance, then you can redraw this circuit as this. Just replace all these capacitors with a single capacitor. And with the same V volt battery, it should be able to draw the same amount of charge. If it draws the same amount of charge, then I can say, okay, this has the same effect as this entire setup. The single capacitor can have the same effect as this entire setup. So then I can call this, the capacitance of this, the equivalent capacitance of this setup. Alright. So from this circuit, also from the equivalent circuit, let's see what do we find from the equivalent circuit. From the equivalent circuit, I can say that Q equals C equivalent times V. Q equals C equivalent times V. Alright, so this is my first equation, this is my second equation. Now all I need to do is equate 1 and 2. Alright, so from 1 and 2, what am I getting? From equation 1 and 2, I will get that I can equate both these Q's and I get that C equivalent equals times V equals V times C1 plus V times C2. And of course I can cancel out all the V's, and finally I have that for parallel combination, C equivalent equals summation of Ci, I going from 1 to n. Please remember again a very important formula which you need to remember. Alright, no excuses about that. Alright, so this is the proof of this. I hope you guys can follow this. A very simple proof, nothing too difficult about it. Alright. So please remember, this should remind you of your class 10th. Alright, when you were talking about series and parallel combination of resistors. So here you're talking about series and parallel combinations of capacitors. Just remember one thing, that only the formula got reversed. The formula that you would apply there for parallel, you apply here for series. The formula that you applied there for series, you apply here for parallel. Okay. Alright, so why don't we get some practice then? Let's remember what we used to do in the resistance problems, and let's apply that here with the new formula, of course. So in this problem, you have to find the equivalent capacitance of the combination shown in the figure. So find the equivalent capacitance of this combination. Alright, please try this, guys. Let's see how much have you learned. Let's see how much attention you were paying. Alright, those of you who are trying can write trying in the chat, by the way, to let me know. Okay, come on, guys, we'll have to wake up. Give me some answers. Come on, I'm waiting. So I think out of all of you who are online, I hope you guys are trying. Okay. Okay, I'm going to give you 2 minutes for this problem. If I don't get any responses in the next 2 minutes, I will solve it. I want you guys to practice it. I keep telling you again and again that whenever I'm giving you a problem to practice right now, please practice right now. I want you guys to get familiar with the problem solving while live with me, so that if you're facing any difficulties, I get to know right away. All right. If you solve problems later and if you get stuck there somewhere, then I won't be there to help you. So I want you to solve this problem right away, so that if in case you're getting stuck, I am right here to help you and I can know where you are going wrong. And you can also realize your mistakes easily. So solve this problem, guys. Alright, find the equivalent capacitance of the combination shown in the figure. Alright, 1 minute is up. I'm gonna wait for another 30-40 seconds maybe. If you don't give me an answer till then I will solve this. I will assume maybe you are having a tough time solving this. Okay, I don't know. There are so many people online, but not even one person responding, or not even one person solving this, which is strange. So do you guys just go to sleep after switching on the lecture? Or is it that boring? Damn. Am I teaching so boring that you started my lecture, you came online, you started watching my lecture, and then my lecture made you fall asleep, or what? Hmm. Alright, so I've waited 2 minutes as promised. Since I'm not getting any responses, so I'm going to solve this. So here, of course, you know that this 40 and this 20 are connected in series with each other, and this is connected in parallel with them. So let's see how I can find this equivalent. So first of all, I need to find the equivalent of this. So I have 40 and 20. So I need to find an equivalent of this. Let's call it C1, C dash. which is the equivalent of 40 and 20. I know 1 over C dash because of the parallel combination. 1 over C dash equals 1 over 40 plus 1 over 20. So I have 40 as my denominator and 1 plus 2 here. So C dash becomes 40 over 3. Alright. So once C dash is 40 over 3, I can rewrite and draw the circuit as. So I have one here. Okay. I have one capacitor here which has a capacitance of 40 over 3. And then I have another capacitor here which has a capacitance of 30. Now these are in parallel, so I know the combination would, the result would be this simple addition for this. So finally C equivalent would be C dash plus 30, and everything is in microfarads. Okay, so I'm not writing micro everywhere, but it is understood that everything is in microfarad. So what am I getting? I'm getting 40 by 3 plus 30. So that is 130 by 3 microfarads. That is the answer. That is my C equivalent. Alright, this is very, very simple. Next, let's just try a slightly more tricky problem. Alright, let's get our hands on trickier problems as we go ahead. So you need to solve this. Find the net charge flown across the battery in the circuit shown. Okay, so here's your circuit. To find what net charge will flow from the battery. Alright. So how can you solve this? It is very easy. You can find the equivalent capacitance of this system, and the charge that will flow from this battery would be C equivalent into 5 volts. I hope you remember that. So let me give you another minute and a half to try this problem. This is slightly tricky. Okay, this obviously is a more complex combination than the last one. But I hope you guys are trying this. Alright, let me just wait 1 minute to see if any one of you gives any response or any one of you is able to solve this. If not, then I will go ahead and solve it. I hope you guys are trying, by the way. Okay, anyhow, why don't I solve this in any case? Alright, so it's very, very simple. Let's just do it here only. So I know these two are in parallel. If these two are in parallel, their equivalent capacitance would be 1 plus 2, which is 3. So here I can draw this as. So stage by stage, I'm going to draw equivalent diagrams for these. So the equivalent of this can be, so 3 plus 3 plus 6 plus 4. Alright, just remember how you used to solve problems in class 10. Replace them one by one. Okay, step by step. So this is 3. This also becomes 3. Why? Because 1 plus 2, that is 3. Parallel combination, we add the capacitances. And this is 6 and this is 4. And this is of course 5 volts. Now let's talk about this also. These 3 are in series. Alright, so since these 3 are in series, I know the equivalent capacitance of these 3. So let's see. 1 over C dash would be 1 over 3 plus 1 over 3 plus 1 over 6. Alright, so what is that giving me? 1 over C dash equals 1 over 6 will be the denominator, 2 plus 2 plus 1. So this C dash I'm getting as 6 by 5. Alright. I hope you guys can see that. Okay. So now I can draw this, the equivalent of this also. Let's draw an equivalent of this. So what I have is, I have two capacitors now. Alright, so one is, how much is it? 6 by 5, so 1.2. This is 1.2 microfarad and this is 4 microfarad. So obviously these two are in parallel, so I can immediately get C equivalent would be 5.2. Once I know the C equivalent, I know the Q, which is what I was asked to find. Q would be equal to C equivalent times 5. Alright, so the answer is very, very simple. C equivalent is 5.2 into 10 to the power minus 6 and into V is 5, so this will be 26. So Q equals 26 microcoulomb. That is the answer that I was looking for. Alright, please have a look. This is very, very simple. You just go and simplify your circuit step by step. So alright, so first you identify this. These two are connected in parallel. You find their equivalent. Then you have three which are in series. You find their equivalent. Then you have two which are in parallel. You find their equivalent. And you have the final equivalent capacitance. Once you have the final equivalent capacitance, the charge that will be supplied by the battery would be C equivalent times the voltage of the battery, which is 5 volt. Alright, so I get my answer as 26 microcoulombs. Alright. So let's try two more problems then. You have to find the equivalent capacitance between points A and B for the following combinations. Alright, so one combination is shown here and one combination is shown here. Alright. So let's see if you can find the equivalent capacitances. Alright, I'll discuss one maybe and one this I would like to discuss the next time. I would want you to have some time to think about this. This is very, very straightforward. This is C and C in a series. So in series, C and C will become C by 2. Alright, so this is very, very simple. I can straight away draw this equivalent. This is A. I can replace this by C by 2. Then C. Then C by 2 and have B. So this will become C by 2, C by 2. Okay. Alright, I hope you can see that. So this is what these three capacitors will look like. The combination of this will come out to be C by 2. The combination of these two will come out to be C by 2. And all of them are in parallel. So C equivalent would be C by 2 plus C by 2 plus C, that is 2C. So this is very, very simple. Alright. Okay, Ankit, no problem. I've already solved this. This is very, very simple. Okay, so one more problem left. So it is this. This appears to be a series, but turns out this is parallel. Alright. See how we do that is, if the potential of this is VA, the potential of this will also be VA. So as long as you're moving along a resistanceless wire, the potential never changes, okay? So the potential of this is also A. Similarly, if the potential of this is B, the potential of this is also B. So you will realize all of them, in all of them, this is at V, this is connected to A, this is connected to B, here this is connected to A, this is connected to B, and here this is connected to A, this is connected to B. So all these plates are essentially connected between A and B only. So though they appear, they have been drawn as, so to appear to be in series, they are actually in parallel. So similarly, C equivalent for the second guy, problem number 2. So if I mark the potentials and if I look carefully, then I will realize all the plates are connected between A and B only. So this gets connected here, and this gets connected here. So since I found that this was B, this was A, and of course this is B. So all my capacitors are connected between A and B only. So the equivalent of this, let's see how we'll make the equivalent of this would be you have A and then you have three capacitors like this. So instead of this complex thing, you have simply this. All three capacitors are in parallel. Since they are in parallel, the equivalent capacitance would be 3C. So that is the answer for this one. So that is how you will start solving these. So why don't you go home and practice some from your HC Verma, maybe try finding the equivalent capacitance of some circuits. Next time we'll talk about some more complex situations, some more complex circuits where we need to find the equivalent capacitance. Alright, so please attend the next class very, very carefully because that is the trickiest part. We will discuss about some complex circuits. Alright, these are still very simple. We will talk about very, very complex circuits. So you need to understand the circuit solving for that. So alright, that is it for today, guys. So go and try some problems of finding C equivalent on your own also. Alright, take up your HC Vermas, practice some problems. Alright, and I hope you followed everything in today's lecture. Alright. Okay. So that is it from my side today, guys. So before I leave, let me remind you that you can get your Unacademy subscriptions following these simple steps. Alright. Go to the plus section, select your goal as IIT JEE and click on that get subscription button there. Alright. Next, when you're getting your subscriptions, if you want to attend my courses, if you like the content that I'm teaching, then you can always use my code RDLive. This code will also give you an additional 10% off. Alright, so please remember that is my code RDLive, Rohit Dixit Live. Alright, so if you like today's video, if you thought you learned some new things, then please press the like button, which most of you have done. And also share this video with your friends. You know that we're providing quality content for absolutely free. So let's hope that more and more students can benefit from this. All right. So you can also press the bell icon to get the notifications of all the lectures and sessions happening on the JEE English channel. And the PDF of all the slides that were used in today's lectures will be available for download in the description box. That download link will be available in the description box by tomorrow. So come back tomorrow and check out. You can download those PDFs also. Please don't forget to join us on the Telegram app to receive all the notifications of all the sessions and lectures happening on the JEE English channel. In case you want to get in touch with me, then my user ID for Telegram is Rohit_Dixit. You can find me on Telegram using this ID and ask any of your doubts or anything that you want to discuss over there. Alright, so that is it. Before I go, let me remind you, if you are getting your Unacademy subscriptions, if you like my videos, if you want to study from me on a regular basis, if you want to join my courses, then you can attend Unacademy. You can get your Unacademy subscription using my code, which is RDLive. Use this code and get an additional 10% off. So I hope to see you guys all on Plus soon. All right. So I'll next see you day after tomorrow, where we'll carry on this discussion. And remember to attend that lecture. It is going to be very crucial. We'll be talking about some complex circuits and problem solving techniques for complex circuits. All right. So see